chemistry again. You have to have an intro to your YouTube video. I know enough about it to know that. Okay, we're gonna look at these slides that are copyright 2000 something McGraw-Hill Company, so don't sue me. Moving on to the next one. Chemistry, matter and change. We're talking today about, go back. Hello, we're talking today about section 2. We already know all this stuff, is why we're moving beyond this. There's our math that we just did. You can find these on your Google Classroom. So, we're talking about section 5.2, quantum theory and the atom. Specifically, we're going to talk about the Bohr and quantum mechanical models of the atom. Are you guys all with me? Yeah. Okay, good. There's your vocabulary. So, it says, Bohr correctly predicted the frequency lines in hydrogen's atomic emission spectrum. The lowest allowable energy state of an atom is called its ground state. When atoms gain energy, it is an excited state. So, electrons can be in one of two states. Ground state, where they normally exist. When we do things like we did in physical science, where we draw atoms and we draw their electrons around them, we draw where they are in their ground state. In fact, we're going to do something in the next session called ground state electron configuration, which is where we draw what all the electrons look like in their ground state. But they can also be excited. And just like you, when you get excited and you start dancing, the electron, when it gets excited, it moves to a higher energy state. So basically, if the, let me just spend a little bit of time drawing this, hopefully. Let me just spend a little bit of time drawing this. Still set to white. There we go. Little nucleus. This is a hydrogen atom, right? There's one electron, one proton. This is the electron's ground state. In an excited state, it would then move to the next energy level up, right? Ground state, energy level 1, excited state, energy level 2. Good? Boop, boop. Back to mouse. Oh, here's an even better drawing of what I just did. So, when an electron is excited, it moves to a higher energy level. So he called the energy level the quantum number. And so for now, it's not quite technically true, but for now, we can think of the quantum number and the energy level as being the same thing. So as you can see, corresponding atomic energy level 1, 2, 3, 4, 5, 6, 7, quantum number 1, 2, 3, 4, 5, 6, 7. You do not have to have memorized the orbital radius or the relative energy. So like I said, in its ground state, hydrogen has one electron in the 1 quantum level, and when it's excited, it moves to the 2 quantum level. So far, so good, right? So what would make an electron, this is what this diagram is helping us figure out, what would make an electron move to a higher energy level? What would excite an electron, right? What excites you is pizza rolls, but what would excite an electron? Just guess. Just based on the words we have on the screen here, guess. It's going to move to a higher energy level, but when it absorbs when it absorbs light. So, and this is where we get something called an atomic absorption spectrum, and then when it goes back to its lower state, it emits that same frequency of light, and that's where we get an atomic emission spectrum. You might remember, and we'll do this in class again, but you might remember the flame tests where we put the different stuff in the fire and the fire turns colors. You should write this in your notebook real quick, but fire, nope, I meant to say the word color is the frequency of visible light, right? The difference, when we see, I'm going to point at things that are in the field of the view of the camera. When we see shark over there that's grayish blue, we see it as grayish blue because that's the frequency of the visible light, right? When we see Dia de los Muertos skull that has many colors, the many colors are because they're different frequencies of visible light. So when we looked at the fire and the fire had changed colors, it's because it was emitting different frequencies of visible light than what we normally see in fire. And that's because those specific elements absorb energy from that frequency, and when they go back to their ground state, they emit the same frequency of energy. So it says, Bohr's model explained the hydrogen spectral lines, but failed to explain any other elements' lines. The behavior of electrons is still not fully understood, but it is known they do not move around the nucleus in circular orbits. So this is the hallmark of the Bohr model of the atom, is that, please write this down. In the Bohr model, they do move in orbit, like planets around a sun. So in the Bohr model, we usually draw it like this. There's the nucleus, here are the electrons.
Bohr model.
So in the Bohr model, sorry, go ahead.
In the Bohr model, electrons.
The electrons orbit just like planets orbiting a star. And we've talked about this before, because I know I've heard you say it. How do the electrons move in real life?
They zip around.
Yeah, when we're being technical, we say that they're excitations of an electromagnetic field around the atom. But we could go as far as to say they pop in and out of existence around the nucleus, right, in a certain area of space. It is now known they do not move around the nucleus in circular orbits. So once again, the Bohr model is where they do move around in circular orbits, but we know that's not true. Like all models, though, are there benefits to thinking of atoms this way? What's one benefit of still using the Bohr model? Yeah, we can count them, right? It might be very hard to count. If we had a truly accurate model of the electrons around an atom, it might be very hard to tell how many electrons there were. They just, right? And very, very quick, too. What else might be easy about this as opposed to the real quantum mechanical or electron cloud model?
It's easy to see the levels.
Yeah, heck yeah. And also we can draw it. Look, I just drew this in like 4.5 seconds, right? If I was going to go to the trouble of drawing what the quantum mechanical model would look like, it would be more difficult, as we're going to see in a second. I'm wiping the annotations. Are you guys ready for that event? Jasmine, you're good?
Mm-hmm.
Okay. So this is how, when I was just saying that we can think of the electrons as excitations in an electromagnetic field, another example we had of excitations in a field was ocean waves. So we can think of electrons as waves. And really, from this slide, that's all I would really like you to write down, is we can think of electrons as waves. Just like we can think of light as a particle or a wave, we can think of electrons as waves. And all of this is talking about how exactly to do that. But at this level, we're not extremely interested in that. Something else that exists and you should be aware of, but that I'm not going to require you to know for your exam, is that there's an equation to relate. You already know what all these things mean probably, and if you don't, you can read it on the slide. But what's this reviewing? What's this mean?
Lambda.
This is lambda, which represents wavelength. H, which is Planck's constant. M, mass, and nu, frequency. So it relates an object, any object, doesn't have to be a particle, any object's wavelength to its mass, right? Because the frequency and Planck's constant are given. Well, Planck's constant is a constant, so it doesn't have to be given. This we should know, though. It says, the Heisenberg uncertainty principle, I'm starting with bullet point 2, the Heisenberg uncertainty principle states that it is fundamentally impossible to know precisely both the velocity and position of a particle at the same time. The way that this is commonly thought of is that any moving object, even if you imagine, catch Hayes, right? I just threw my, I don't know what you call it, Promethean pin at Hayes. If we, in order to describe its velocity, right, it has to be doing what? What does it have to be doing in order for us to describe its velocity? Moving, yeah. Only moving objects have a velocity. In order to perfectly describe its position, is there a way that if I told you, show me this in its path, is there a way I can tell you to represent this perfectly in its path in the air? If you had to, though, like if I said, well, like if I took a picture, right? If you had your phone out and you took a picture of this, you could tell me what its position was at exactly that second, right? But could you tell me its exact velocity from just that picture? No. So that basically for any moving object, it's fundamentally impossible, but especially for small subatomic particles, it's impossible to know both its velocity and its position at the same time. We can know one or the other, but we can't know both. And then because of that, because of the Heisenberg uncertainty principle, all we can know is the probability that an electron will be around a certain area, right? So we can't say, as opposed to the Bohr model, we can't say, this is where the electrons will be. They'll be in an orbit. We just can't say that because we can't know their position and their velocity. All we can know is the probability at which they will occur. And so, due to that, we're going to just skip that for now. Due to that, we come up with the quantum mechanical model, which is also sometimes called the electron cloud model. So this is what we would have. This is still not a perfect representation. What are some inaccuracies about this model? Like what's this is representing an atom and the electrons around it. What are some inaccuracies about this? Just the diagram. Oh. Well, for one thing, it's too big or it's too small. And for another thing, these aren't blue, right? There's not a million of them. So there's some fundamental flaws with any model, and we'll talk about that next time. Bye!